Hello everyone, welcome to today's video on PySpark. In this video, we're diving into one of the core strengths of PySpark distributed data processing. PySpark harnesses the power of Apache Spark's distributed computing framework, allowing you to process massive datasets across clusters efficiently. Whether you are dealing with big data in the cloud or on a local cluster, understanding how PySpark handles distributed data is essential for optimizing performance and scalability. Stay tuned as we explore how PySpark manages everything from partitioning to fault tolerance and in-memory processing, making it a go-to solution for big data applications. Introduction. PySpark is the Python API for Apache Spark, enabling Python developers to efficiently process large datasets across distributed clusters. By abstracting the complexities of distributed systems, PySpark provides a high-level API for data manipulation and analysis. It splits large datasets into partitions for parallel processing across multiple nodes, automatically handling task distribution, resource management, and fault tolerance. This makes PySpark a powerful tool for big data processing, machine learning, and real-time data analysis in Python. 1. RDD resilient distributed datasets. Resilient distributed datasets (RDDs) are the core data structure in PySpark, representing distributed collections of data that can be processed in parallel across a cluster. RDDs allow large datasets to be split into partitions and distributed for efficient processing. They are fault tolerant, meaning they can be recomputed if a node fails, using lineage information that tracks how the RDDD was created. RDs support two main operations transformations like map and filter, which define how data is processed, and actions like count and collect, which trigger actual computation. Both types of operations are distributed across the cluster, enabling PySpark to efficiently handle large-scale data processing. Practical examples. This PySpark code demonstrates the creation and manipulation of an RDDD resilient distributed dataset using transformations and actions. The RDDD is created from a simple list of numbers data ranging from 1 to 10. The sc.parallelize function is used to distribute the data across the cluster, splitting it into 4 partitions as specified by the numSlices parameter. This ensures that the data is distributed across multiple worker nodes, allowing for parallel processing. The first transformation applied to the RDD is the map function, which multiplies each element of the RDD by 2. This transformation doesn't immediately execute but builds a logical plan of what needs to be done when an action is triggered. After this, the filter transformation is applied, which keeps only the elements greater than 10. Again, this transformation is lazy and waits for an action to execute. The code then triggers two actions. The first is collect, which executes the transformations and brings the results back to the driver program. It returns the elements that remain after the transformations, which are all the values greater than 10, i.e. 12, 14, 16, 18, 20. The second action is count, which also triggers execution and returns the number of elements in the filtered RDD. The count action here returns 5 because there are 5 elements greater than 10 after the transformations. Finally, the results are printed. The collect action gives the list 12, 14, 16, 18, 20, and the count action shows that there are 5 elements left after the filtering operation. This example demonstrates how PySpark transformations like map and filter work in conjunction with actions like collect and count to process data in a distributed manner. 2. Partitioning data. Partitioning is a key feature of PySpark that enables efficient distributed data processing. When you create an RDDD or data frame, PySpark automatically divides the data into partitions, which are chunks of data spread across different nodes in the cluster. Each partition is processed independently by the worker nodes, allowing multiple tasks to run in parallel. This parallelism is what makes PySpark capable of handling large-scale data processing with speed and efficiency. Partitioning plays an essential role in optimizing performance because it allows Spark to distribute the workload evenly across the cluster. Instead of processing the entire dataset on a single machine, PySpark breaks it into smaller pieces, each handled by different nodes simultaneously. This reduces the time required to perform computations and enables scalability, meaning the system can handle larger datasets as more resources nodes are added. You can control the number of partitions when creating an RDD by specifying the numSlices parameter as shown in the previous example, or by adjusting it based on the size of the dataset and the available cluster resources. Proper partitioning ensures efficient use of cluster resources and faster execution of tasks, as each node processes only a portion of the data at a time. Practical examples. This PySpark code demonstrates the process of creating an RDDD with custom partitioning and applying transformations on the data within each partition. The RDD is created from a list of numbers ranging from 1 to 10, and the sc.parallelize function is used to distribute the data across 4 partitions specified by the numSlices parameter. By explicitly setting the number of partitions, you can control how the data is split across the cluster's worker nodes, ensuring better load balancing and parallelism. The code first checks and prints the number of partitions using the getNumPartitions method, which confirms that the data has been divided into 4 partitions. Each partition contains a portion of the data roughly an even split of the original list. The map partitions transformation is then applied to process each partition independently. In this example, a function process underscore partition is defined, which takes an iterator as input representing the data in a partition and returns the sum of the values within that partition. The map partitions transformation applies this function to each partition of the RDD, and the result is an RDD containing the sum of the elements from each partition. Finally, the collect action gathers the results from all the partitions and returns them to the driver program. The results are printed showing the sum of the numbers in each partition. This example illustrates how PySpark allows you to process data independently within each partition, leveraging parallelism to speed up computation. Partitioning ensures that tasks are distributed across the cluster, making PySpark highly efficient for processing large datasets. 3. Transformations and actions. In PySpark, transformations like map, filter, and flatmap are lazy operations that define the data processing steps but don't execute immediately. Instead, they build a logical execution plan known as a DAG, which is only triggered when an action is called. Actions like collect, count, and save as text file trigger the actual execution of the transformations. When an action is invoked, PySpark sends the tasks to the cluster nodes for parallel processing, executes the transformations, and returns the result. This separation allows PySpark to optimize workflows, ensuring efficient data processing. Practical examples. This PySpark code demonstrates how transformations and actions work in PySpark through a simple example using an RDD. The code begins by creating an RDD from a list of numbers 1 to 10 using the sc.parallelize function. This RDD will be distributed across the Spark cluster for parallel processing. Next, the code applies two transformations on the RDD. The first transformation map multiplies each element in the RDD by 2. However, at this stage, the computation is not executed immediately. PySpark uses lazy evaluation, meaning that the map transformation only defines what needs to happen without performing the actual computation. The second transformation, filter, is applied to the result of the map transformation. It filters out elements, keeping only those greater than 10. Again, no computation occurs yet, as the transformations are stored in a logical plan. After defining the transformations, two actions are performed which trigger the execution of the entire transformation pipeline. The first action collect triggers the execution and brings the filtered results back to the driver node. This action causes Spark to execute both the map and filter transformations on the cluster and return the final result, a list of numbers greater than 10, which in this case is 12, 14, 16, 18, 20. The second action count also triggers the execution but instead returns the number of elements remaining after the transformations. This action performs the same computations but only returns a count of the filtered elements. In this case, the result is 5 since there are 5 elements greater than 10. Finally, the results are printed, demonstrating how PySpark processes the data in parallel when actions are called, leveraging transformations to build a logical plan, but only executing the computations when needed. 4. Task distribution and scheduling. In PySpark, task distribution and scheduling are crucial for efficient parallel processing across a cluster. The Spark context is responsible for communicating with the cluster managers such as Yarn, Mesos, or Kubernetes to request resources such as CPU and memory and to distribute tasks across the cluster. This process ensures that the workload is divided among the available worker nodes for parallel execution. Task distribution involves breaking down the work into smaller units called tasks, which are the smallest executable units in Spark. These tasks are sent to executors running on the worker nodes. Each executor is responsible for processing a specific partition of data, allowing the tasks to run in parallel across different nodes. This parallelism enables Spark to process large datasets efficiently and reduces the overall time required for computation. The DAG directed acyclic graph scheduler plays a key role in managing the logical execution plan of a job. When a job is triggered by an action, PySpark creates a DAG to represent the sequence of transformations and actions. The DAG scheduler then breaks down the job into stages and tasks. These stages are based on shuffle boundaries points where data needs to be reorganized or shuffled between nodes. Once the job is divided into stages, the DAG scheduler distributes the tasks within each stage to the worker nodes for execution. Stages represent a group of tasks that can be executed in parallel, while tasks are assigned to executors to process partitions of data within each stage. By dividing the job into stages and tasks, PySpark ensures that the workload is distributed evenly across the cluster and that the job is executed efficiently. This approach allows Spark to handle large-scale data processing tasks with speed and scalability, making it an ideal solution for big data environments. Practical examples. This PySpark code demonstrates how task distribution and scheduling work in a distributed computing environment. It starts by creating an RDD from a dataset of numbers ranging from 1 to 100 using the sc.parallelize function. The data is split into 4 partitions, allowing Spark to distribute the workload across multiple nodes for parallel processing. The first transformation applied is the map function, where each element in the dataset is mapped to a key value pair. In this case, the function groups numbers by their even or odd status by returning a tuple x%2 x, where x%2 serves as the key and x is the value. This results in key value pairs where the key is either 0 for even numbers or 1 for odd numbers, effectively grouping the dataset into two categories, even and odd numbers. The next transformation is reduce by key, which introduces a shuffle operation and creates stages within the job execution. The shuffle process involves redistributing data across the partitions based on the keys even or odd. Each partition will group the numbers by their key and then apply the reduce by key function to sum the values for each key. For example, all the even numbers are grouped under the key 0 and the odd numbers under the key one. The reduce underscore function sums the values in each group. Finally, the action collect is called, which triggers the execution of the transformations. At this point, Spark sends the computation task to the executors on the worker nodes, where they process the partitions in parallel. Once the tasks are completed, the results are collected and brought back to the driver program. The final output is printed showing the sum of even numbers grouped under key 0 and the sum of odd numbers grouped under key 1. The result might look like 0, 2550, 1, 2500, where 2550 is the sum of even numbers and 2500 is the sum of odd numbers. This example demonstrates how PySpark uses transformations and actions to process data in parallel with task distribution and scheduling handled by Spark's execution engine. The shuffle introduced by reduce by key creates stages, ensuring the data is correctly grouped and processed across the cluster. 5. In-memory processing. One of PySpark's key strengths is its in-memory processing, which allows RDs to be cached in memory, reducing the need for repeated disk access during computation. This is especially beneficial for iterative algorithms like machine learning or data analysis, where the same data is accessed multiple times. By caching data in memory, PySpark speeds up processing and avoids unnecessary I/O operations. Users can manage caching using the cache or persist methods, making PySpark highly efficient for big data tasks that require fast, repeated access to the same dataset. Practical examples. In this practical example, we demonstrate the performance difference between computations with and without caching in PySpark using a large dataset of numbers from 1 to 10 million. First, we create an RDD by parallelizing the dataset across the cluster and then apply a simple transformation using the map function where each element is multiplied by 2. In the first case, we perform two sum actions on the transformed RDDD without caching. Since PySpark uses lazy evaluation, the actual transformation is only computed when an action like sum is triggered. However, because the RDD is not cached, PySpark has to recompute the entire transformation from scratch each time we run the sum action. As a result, both sum actions take similar amounts of time, since PySpark is effectively repeating the same work twice. In the second case, we apply caching to the RDD after the transformation using the cache method. This tells PySpark to store the transformed RDDD in memory after the first computation. When we run the first sum, PySpark performs the transformation and stores the result in memory. For the second sum, instead of recomputing the transformation, PySpark retrieves the data directly from memory, significantly speeding up the process. By comparing the execution times, it becomes clear that caching provides a substantial performance improvement. Without caching, PySpark must recompute the transformation for every action, whereas with caching, the data is stored in memory and can be quickly accessed for subsequent actions. This example highlights the value of PySparks in memory processing, especially for iterative algorithms or multiple actions on the same dataset, where caching can save both time and computational resources. 6. Fault tolerance. PySpark's fault tolerance ensures that computations can recover from failures without losing data. It achieves this through resilient distributed datasets (RDDs), which maintain a lineage of transformations. If a node fails, PySpark can recompute only the lost partitions based on the lineage rather than rerunning the entire computation. Additionally, PySpark automatically retrieves failed tasks and reschedules them on available nodes, ensuring reliable execution of large-scale data processing jobs even in the face of hardware or network issues. Practical examples. This PySpark code illustrates how Spark's fault tolerance mechanism works by leveraging lazy evaluation and lineage to handle potential failures in distributed systems. First, the code creates an RDD from a list of numbers 1 to 10 and divides the data into four partitions using the sc.parallelize function. The dataset is then transformed with a map operation that multiplies each number by 2. However, due to PySpark's lazy evaluation model, the transformation does not execute immediately. This delayed execution allows PySpark to optimize the logical execution plan before performing any computations. Next, the code demonstrates how PySpark's fault tolerance works in case of data loss or failure in a distributed system. Although no action is initially triggered, once an action like collect is called, Spark will process the transformation and apply the map operation to each partition. If a failure occurs and some partitions are lost, PySpark can recover those lost partitions using the lineage of the RDD. This lineage is essentially the history of transformations applied to the original data, allowing Spark to recompute only the lost partitions rather than the entire dataset. Finally, the collect action is triggered, causing PySpark to execute the transformation and return the results, multiplying each number in the dataset by 2. Even if a partition were lost, Spark would automatically recover and recompute the necessary partitions to provide the correct result. The output shows the final result after recovery, confirming PySpark's fault tolerance by ensuring that data processing can continue without loss, even in the event of failure. 7. Data locality. Data locality is an important optimization in PySpark, where tasks are executed on the same worker nodes where the data is stored. This reduces the need to transfer data over the network, minimizing overhead and improving performance. By processing data locally, PySpark speeds up task execution and makes more efficient use of resources. If data must be transferred, it incurs additional costs, so data locality helps optimize distributed computations by minimizing network communication. Practical examples. This PySpark code demonstrates how data is partitioned, processed, and transformed in a distributed environment. With a focus on data locality and efficient word counting, the RDDD is created from a list of sentences which is distributed into four partitions using the sc.parallelize function. By splitting the data into partitions, PySpark enables parallel processing across multiple worker nodes in the cluster. The code begins by confirming the number of partitions using the getNumPartitions method, which shows that the data is divided into four chunks, allowing for parallel task execution. Next, the flat map transformation is applied to split each sentence into individual words. This transformation ensures that each partition processes the data in parallel, breaking the text into smaller, manageable units words. Afterward, the map transformation creates key value pairs where each word is paired with the number 1. This step is crucial for the upcoming word count as it initializes the word frequency by assigning an initial count to each word. To count the occurrences of each word, the reduce by key action is applied. This operation groups the key value pairs words across the partitions and sums the counts for each unique word. Because reduce by key involves shuffling data across partitions, PySpark tries to maintain data locality by keeping the task close to where the data is stored, minimizing unnecessary data movement across the network. Finally, the collect action retrieves the word count results back to the driver program. The result is a list of words and their corresponding counts, which are printed for verification. This example highlights how PySpark uses parallel execution and data locality to efficiently process data and minimize overhead, ensuring fast and scalable computations across distributed systems. 8. Broadcast variables and accumulators. Broadcast variables in PySpark allow for efficient sharing of large, read-only data across worker nodes by sending it only once and catching it locally on each node. This minimizes network overhead and improves performance, especially for large datasets like lookup tables that are needed across many tasks. Each task can access the broadcasted data directly from memory, ensuring faster computations. Since broadcast variables are read only, they provide consistent, unmodifiable data to all tasks, making them ideal for use in distributed processing. Practical examples. Practical examples. This PySpark code demonstrates the use of a broadcast variable to efficiently share a lookup table across all worker nodes in the cluster. The dataset consists of a list of fruits apple, banana, orange, banana, apple, which is split into three partitions using the sc.parallelize function. This partitioning enables parallel processing across different worker nodes in the cluster. The code introduces a lookup table as a Python dictionary that maps each fruit to a corresponding value apple 1, banana 2, orange 3. This lookup table is broadcasted to all worker nodes using sc.broadcast. By broadcasting the lookup table, PySpark ensures that the data is sent only once to each node and then cached locally, avoiding repeated data transfers across the network. This is especially useful when you need to reference the same data across multiple tasks. Next, the code applies a map transformation to the RDD, where each fruit is mapped to its corresponding value from the broadcasted lookup table. The broadcast variable broadcast underscore lookup underscore table dot value is used to access the dictionary, ensuring that each task can efficiently retrieve the values without needing to resend the data from the driver. Finally, the collect action is called to gather the results from the worker nodes and return them to the driver program. The result is a list of tuples where each fruit is paired with its corresponding value from the lookup table, demonstrating how the broadcast variable allows for efficient distributed use of the lookup table. The output is printed as mapped result using broadcast variable apple 1 banana 2 orange 3 apple 1 orange 3 banana 2 1 orange 3 banana 2 apple 1. This example illustrates how broadcast variables help optimize performance by reducing network overhead and ensuring efficient access to shared data in distributed computations. That's a wrap on how PySpark handles distributed data processing. We've covered how PySpark splits data into partitions, distributes tasks across nodes, leverages memory processing, and ensures fault tolerance, all key components that make PySpark so powerful for large-scale data applications. If you found this video helpful, make sure to give it a thumbs up, subscribe to our channel, and hit the notification bell for more PySpark tutorials and interview prep videos. As always, feel free to drop your questions in the comments, and I'll see you in the next video.